Hey folks, welcome to another set of Chemistry 2 video notes. Today we're going to cover Chapter 11, which is all about the ideal gas law. In order to talk about the ideal gas law, we first need to be able to describe the gas phase. Then we can talk about the ideal gas law, how to manipulate it to solve for a number of different gas properties, and why the ideal gas law isn't exactly ideal. Let's get started. Scientists have studied the properties of gases for ages. Three of the most famous contributors to our current understanding of gas behavior were Robert Boyle, Jacques-Alexandre Charles, and Amedeo Avogadro. Yes, that Avogadro. Boyle studied the relationship between the pressure of a gas and its volume. Charles studied the relationship between the volume of a gas and its temperature. And Avogadro studied how the volume of a gas is affected by the number of gas molecules present. In order to understand gases and approximate their properties mathematically, we have to get our headspace into a fictional world where gases behave ideally. For a gas to behave ideally, we have to assume that the particles of the gas have absolutely no volume, that they just exist as single points in space. We also have to assume that these particles fly around in straight lines until they collide with something, only changing directions upon collision. We also have to assume that all of the collisions of the particles are elastic, meaning that there's no energy lost through heat or work when the particles collide. Lastly, and probably most importantly, we have to assume that there are absolutely no intermolecular forces of attraction between the particles. That's a lot of assumptions to make, but making these assumptions really helps us to relate the different properties of a gas all into one simple equation. We're going to continue on with these assumptions until the last section of this chapter, but keep it in the back of your mind that an ideal gas is simply a model. If a gas were to actually behave ideally, meaning there are no forces of attraction between the molecules, there would be no temperature cold enough to cause those gases to condense into a liquid or solid. That's obviously something that doesn't happen. No gas actually behaves perfectly ideally. Some gases come extremely close, especially at very high temperatures or very low pressures. And then most gases, except at very low temperatures, behave pretty ideally. So the ideal gas law gives us a good approximation of the properties of a gas. In order to get to the ideal gas law, we have to know about the properties that make it up. There are only 4 variables you have to worry about: pressure, volume, number of molecules, and temperature. If you know any 3 of those properties, you can mathematically solve for the 4th. Pressure is defined as the amount of force applied to a unit of area. It's most frequently measured in atmospheres or millimeters of mercury. Sometimes it's measured in bars, torrs, or pascals. Volume is the amount of space the gas will take up, and it's usually measured in liters. The number of molecules, or N, is measured in moles, and temperature can be measured in Kelvin, degrees Celsius, or degrees Fahrenheit. Since our air is made up of gas particles, those particles are constantly hitting objects. When those collisions occur, a force is applied to the object the particles are hitting. This is what pressure is. The force exerted by our air on any object is called the atmospheric pressure, or the air pressure. We now measure it with a barometer, but originally we measured it with a mercury tube. When the empty and open tube, kind of like a straw, is placed in a dish of mercury, the mercury does not rise up the tube on its own, because the air pressure inside the tube is forcing the particles down just as much as the air pressure outside the tube is. When we pump the air out of the tube, we create a vacuum. In a vacuum, there are no particles, therefore no collisions and no air pressure. In this case, since there's no air pressure inside the tube to push the mercury down, the force of the air on the mercury in the dish pushes the mercury up into the tube. We find that generally at sea level, the mercury will rise to about 760 millimeters. This is where we get the unit for millimeters of mercury. The normal atmospheric pressure of 760 millimeters of mercury could also be defined as 1 atmosphere. To really grasp the idea of atmospheric pressure, think about a metal can. When the can is open and the air pressure is equal inside and outside of the can, the walls of the can feel no net pressure because the air is able to push equally on both sides of each wall. If we remove the air from inside the can, there's no particles to push the walls of the can out. There's no air pressure to counteract the pressure from outside of the can, so the can will end up crushing in on itself. The other variables are pretty short and sweet to summarize. Temperature is just the temperature of the gas. For our purposes with the ideal gas law, we tend to measure the temperature in units of Kelvin. To find the temperature in Kelvin, we just add 273.15 to the degrees Celsius temperature. For volume, since a sample of a gas does not have a definite volume, it fills whatever container it's in. Therefore, the volume of a sample of a gas would just be equal to the volume of the container that holds it. This is not the same for our condensed phases of liquids or solids. They have their own distinct volumes. If we transfer a certain amount of liquid from a small container to a larger container, it takes up the same amount of volume. If we do the same for a gas, the volume will change to match the volume of the container. Finally, the number of particles, or lowercase n, is simply how many gas molecules we have. Since these usually exist in very large quantities, we measure these in moles instead of molecules. There are 3 simple rules that Boyle, Charles, and Avogadro figured out about the behavior of gases. To really understand those rules, you have to understand that pressure is directly related to the number and the force of collisions of particles against the walls of their container. The more or harder the collisions are, the higher the pressure. So rule number 1 is that the pressure is inversely proportional to the volume. In other words, it's directly proportional to the inverse of the volume. As the volume decreases, there will be less wall surface area for the particles to hit, meaning the same amount of collisions happen overall, but they take place in a smaller area, causing more force per area or a higher pressure. If the volume increases, there's more wall space for the particles to hit. So the same amount of collisions get spread out over a larger area, creating a lower pressure. Rule number 2 tells us that the pressure is proportional to the temperature. If you remember from way back in Chapter 7, temperature is related to the thermal energy of particles, or their speed. If we have higher temperatures, the particles will be moving faster. When they move faster, they hit the walls of the container with a greater force, causing a higher pressure. Slower moving particles hit the walls with less force because they're not moving as fast. Therefore, they create a lower pressure. And rule number 3 states that the pressure is proportional to the number of molecules. If you keep the same volume and the same temperature but add more particles to your container, there will be an increase in the number of collisions against the walls, which increases the pressure. If you have fewer particles, you'll have fewer collisions and a smaller pressure. Basically, it all comes down to the frequency and the force of collisions. If you can grasp that idea, the whole concept of the ideal gas law should click pretty easily. So if we take all 3 of those relationships and smush them together, we see that the pressure is directly proportional to the number of particles and the temperature, and the inverse of the volume. In order to make that an actual equation, we have to add in a proportionality constant that makes it a true equality. This constant is known as the ideal gas constant, and it's labeled as a capital R. There are a few different R values we could use based on the units we need, but the one we're going to use most often is R equals 0.0821 liters atmospheres per mole Kelvin. When we put this together, P equals nRT divided by V, or as you're likely familiar with, PV equals nRT. This is the ideal gas law. With the ideal gas law, we can solve for a multitude of different properties. If we want to know any one of our 4 variables and we have the other 3, we just plug them into our equation and solve for the missing variable. If we've used combustion analysis to find the empirical formula of a substance, but we want to know its molar mass, we can use the ideal gas law to find that. Since we know that the number of moles is equal to PV over RT, and we also know that the number of moles of a substance is equal to the mass of the substance divided by its molar mass, we can substitute those equations in together. The only extra thing we need to know is the mass of our gaseous substance before we put it through combustion analysis. So when we replace that second equation with the n in the first equation and solve for the molar mass, we get that the mass of the sample times R times T divided by P and V gives us the molar mass of our gas. Also, since we know that density is just mass over volume, we could find the mass of our original sample divided by the volume of our sample to find its density. If we don't know the mass of our original sample, but we know its identity and therefore its molar mass, we could do a little bit of algebra with that equation and find that the molar mass times the pressure of the gas divided by its temperature in the ideal gas constant will give us the gas's density. Finally, if we want to compare the properties of our gases under 2 different sets of conditions, we have an equation for that. Since we know that R is constant, we can solve for it and find that R equals PV over MT. Since the R will remain the same for any set of conditions for a gas, we can set PV over NT of one set of conditions, say the initial set of conditions, equal to that of a second set of conditions, or the final set of conditions. Sometimes we notate these with subscripts F and I for final and initial, or we could also use subscripts of 1 and 2 for the first set of conditions and the second set of conditions. Either way, if we know all but one of these variables, we can manipulate the equation to find the missing one. No matter which of these types of problems you're doing, the most important thing is to always, always, always write out your units and make sure they cancel appropriately. If we consistently used our 0.0821 liters atmospheres per mole Kelvin for R, we have to make sure that our volume is in liters, our pressure is in atmospheres, N is in moles, and temperature is in Kelvin. To solve the initial final condition problems, first list all of the P, V, N, and T values that you're given for both the initial and final conditions. If any conditions remain the same both before and after, we can write them as an equality. We can say that the initial equals the final for that property. Since they're on opposite sides of our equation, they'll end up canceling each other out since they're equal to each other. Then you write down your expression, cross out any of those conditions that don't change, and then rearrange your equation to solve for the variable you're looking for. Plug in the numbers you have, make sure your units cancel appropriately, and then punch it in a calculator, and that's it. Alternatively, you could just write out all of the conditions you're given, solve your expression for the variable you're looking for, then plug all the numbers in. Either way, it should get you to the correct answer as long as all of your unneeded units cancel out. If you run across a problem that gives you a set of conditions at STP, that stands for standard temperature and pressure, which is defined as a temperature of 273.15 Kelvin and a pressure of 1 atm. If we plug those values into our ideal gas law, we'll see that at standard temperature and pressure, 1 mole of any gas will occupy a volume of 22.4 liters. Let's do some examples. All right, say you're told about an experiment in which someone heats a sealed 2-liter glass vessel containing 0.1 moles of a gas until it explodes. So already we know that my volume is 2.0 liters and my number of moles is 0.1. When they heated this up, it happened to reach a temperature of 600 degrees Celsius before it exploded. The experiment was to determine the pressure that the vessel could withstand. So the pressure is what we are looking for. Because R is a constant and it is always 0.0821 liters atmospheres per mole Kelvin. So we write down all of our information, we make sure that our units work, and right now I've got Kelvin in my R value, but I've got degrees Celsius up here. So I need to convert that to Kelvin by adding 273.15, and that gets me 873.15 Kelvin. Our equation, P equals nRT over V, only has the 4 variables, P, V, N, and T. And we know 3 of those 4, so we just plug them in. We get P equals 0.1 moles times 0.0821 liters atmospheres per mole Kelvin times 873.15 Kelvin, all divided by the volume, which is 2.0 liters. Now you might notice we have moles here and moles there, so that cancels out. Liters up top, liters on bottom, so that cancels out. Kelvin and Kelvin, so that cancels out, and we're left with atmospheres, which is the unit of pressure, and that's what we're looking for. When you punch those numbers into the calculator, you should get that the pressure before the vessel exploded was about 3.6 atmospheres. All right, next, say we wanted to figure out how many moles of helium there are in a balloon that we just filled up. The balloon is at room temperature, 22 degrees Celsius. Convert that to Kelvin, and we get that our temperature is 295.15 Kelvin. There's a barometer in the room which says that our air pressure is 748 millimeters of mercury. Now, that means that the pressure pushing on the balloon is 748. Since balloons are elastic, they have elastic walls, they're going to push out, they're going to stretch, or they're going to contract as much as they need to get the air pressure inside the balloon to be the same. So we can assume that this is also the pressure inside of our balloon. Let's convert that to atmospheres. We know that there are 760 millimeters of mercury for every 1 atmosphere, which gives us a pressure of 0.984 atms. To find the volume of the balloon, we decide to use the properties of water displacement, and we stick it in a big tub of water and find that it displaces 240 milliliters of water. We need that in liters, and we know that there's 1,000 milliliters for every 1 liter, so our volume is 0.240 liters. Now, we have all that we need to know to find the number of moles. Remember, we're looking for N, and R is, for your purposes always, 0.0821 liters atmospheres per mole Kelvin. So plug this into our equation. It's P equals nRT over V. Or if you remember the equation better this way, that might be a simpler step. We're looking for N, so if we divide by RT on both sides, then N equals PV over RT. Plug our numbers in. We get N equals pressure of 0.984 atmospheres times the volume of 0.24 liters, all divided by 0.0821 liters atmospheres per moles Kelvin, times our temperature, which is 295.15 Kelvin. Now, before you take the time to punch it in your calculator, make sure the units cancel out right. We have atmospheres on top, atmospheres on bottom, liters on top, liters on bottom. On the bottom half of our equation, we have Kelvin on top, Kelvin on bottom, so that cancels. And we have a fraction inside of a fraction with moles on bottom, so that means the moles moves up to the top, and that's what we're looking for. So if we punch that in the calculator, we get that there are 0.01 moles of our gas inside of our balloon. From there, if we knew that that gas was helium, we could find the mass of our balloon, since we know that the number of moles divided by the molar mass is equal to the mass. How about going about finding the molar mass of a gas? Say we found that our gas has a mass of 0.125 grams, and that's before we take it through combustion analysis. We had it stored in a 0.1 liter container, and we had a pressure of 0.0728 atmospheres. We also had a temperature of 298.15 Kelvin. If we plug that into our equation, we know, let's see, our equation is molar mass equals the mass of our sample times R times T divided by pressure times volume. So plug our numbers in. Molar mass equals 0.125 grams times 0.0821 liters per atmosphere mole Kelvin times temperature 298.15 K divided by the pressure 0.728 atmospheres and the volume, which was 0.10 liters. Double check that our units cancel. We get atmospheres on top, atmospheres on bottom, Kelvin on top, Kelvin down here, liters up top, liters down here, and we'll get grams per mole. If we punch that in, we get that the molar mass is 42.0 grams per mole. Now, I said we did combustion analysis on this gas. We did all of that work, found our percentages for each element, and found that our empirical formula was CH2, which has a molar mass of about 14 grams per mole. So we would take our actual molar mass divided by our empirical molar mass, and we get that it's about 3 times as large of a molecule. So then our actual molecule is C3H6. Let's say we had a balloon filled with carbon dioxide, which, as we know, has a molar mass of about 44.009 grams per mole. Our balloon had a pressure of 0.99 atmospheres and a temperature of 295.15 Kelvin. This is all we need to know to find the density. Remember, density equals mass over volume. From our previous equation, we had the molar mass equals the mass of the sample times R times T over PV. So if we wanted to solve for mass over volume, we just times by P over RT on both sides, and we find that our mass over volume is equal to the molar mass times the pressure divided by RT. And again, mass over volume equals density. So if we plug our numbers in, we have our molar mass is 44.009 grams per mole times the pressure, which was 0.99 atm, divided by the R, which is 0.0821 liter atmosphere per mole Kelvin, and also divided by our temperature, which is 295.15 Kelvin. Go through and double check our units. We have Kelvin here, Kelvin there, atmospheres on bottom, atmospheres on top, moles on the bottom of the bottom, and moles on the bottom of the top, so that cancels out. And we're going to end up with grams per liter. So when we do that, we find that our density is equal to about 1.80 grams per liter. All right, for our final problem today, we're going to look at the difference between one set of conditions and the other. So let's say I have a gas at an initial pressure of 5 atms and an initial temperature of 200 degrees Kelvin. That gas is kept in a rigid container, so my initial volume is going to equal my final volume, and I don't change the number of moles that I have, so my initial moles is equal to my final moles. It tells us I want to increase the temperature to 400 degrees Kelvin. What is my final pressure? A lot of times, especially when I'm working out examples myself, I'll use P1 and P2 instead of PI and PF. Doesn't matter which one you use as long as you're keeping track of which one's which. So our equation is the initial pressure times the initial volume divided by the initial number of moles times the initial temperature is going to be equal to the final pressure times the final volume divided by the final number of moles times the final temperature. Now we just said since the volume does not change, we can cross it out because it's going to be equal on both sides. It'll just cancel itself out. And so does the number of moles. So my actual equation, or the simpler version of my equation, is just Pi over Ti equals Pf over Tf. I want to solve for the final pressure, so I'm going to multiply by the final temperature on both sides. And I get that my final pressure is equal to the initial pressure times the final temperature divided by the initial temperature. So that's going to be 5 atms times my final temperature, which was 400 Kelvin, divided by my initial temperature, which was 200 Kelvin. And I get that my final pressure is about 10 atms. If you'll remember from before, the ideal gas law is just a model for how gases behave in general. In most cases, it gives us a fairly close approximation to their actual values, but it's important for you to know that it's just that, an approximation. As you can see on these graphs, the gases listed here behave very close to ideally at very low pressures, like less than 10 atm. As our pressure gets higher, the graphs get less ideal. Well, why is that? Well, there's no gas that exhibits absolutely zero intermolecular forces, and all gas particles obviously have some volume of their own. Therefore, no gas actually behaves 100% ideally 100% of the time. This is why the ideal gas law is a simple approximation. We've developed far more advanced equations to help correct for the non-ideal behavior of gases. The first and simplest of which is the van der Waals equation. Johann Diedrich van der Waals was a Dutch physicist in the late 19th century and early 20th century. He developed this equation. You might have seen his name before when we talked about intermolecular forces like LDFs, dipole-dipole, and hydrogen bonding, as those forces are collectively called the van der Waals forces. Anyway, this guy recognized that our two basic assumptions for the ideal gas behavior are simply untrue, so he created this equation with some new constants that are different for each gas. The A term in this equation corrects for the attractive forces between our gas particles. If our gas particles are attracted to each other, they're going to slow down when they come near each other, causing them to hit the walls with less force and giving us a lower than expected pressure. Therefore, we have to add in this term to our measured pressure to make it equal to the ideal pressure. The A constant is measured in atmospheres times liters squared over moles squared, and we multiply it by the number of moles divided by the real volume squared. Since our particles do take up their own space, the actual available volume of our container turns out smaller than what we're measuring it. So to show that, we subtract the volume of the particles from the volume of our container. This B term is measured in liters per mole. If you're asked to do any problems with this equation, you'll be given the A and B constants as well as all of the other conditions except the one you're solving for. At that point, it's just a plug and chug and a little bit of algebra. The main focus of this chapter is working with the ideal gas law, so expect a lot more practice with that than this van der Waals equation. Well, that's all for today, folks. I hope this video helps you on your way to mastering the behavior of gases, both conceptually and mathematically. As always, if you have any questions, let me know.